Good afternoon, everyone. I welcome you all to the final week. I welcome you all to the final week, week 12, for Analog Electronic Circuits course. Today being the final week, I would like to wish you all the best for the coming exams, and hope this session helped you in some way to deal with this particular course. So in today's session, we'll be solving problems based upon voltage regulators. So if we look carefully, at this particular circuit, so what happens is the circuit helps in regulating the voltage, and most commonly the line regulation that we call. So it helps in line regulation. That means any power supply, any disturbance in the power supply will not be affecting the output of the output through this op-amp. As here, let's say the voltage across this diode is Vx, then the output that we will get is 1 plus R2 upon R1 into Vd, that is the difference voltage. Now coming to this particular question, here what is given, that the circuit below is a voltage regulator. A dirty supply with ripple and noise is regulated into a clean supply with the help of the feedback circuit that is shown below. Now here assume that the gain of op-amp, so now moving forward with the solution, so it is given that the gain of op-amp, that is open loop gain, is 1319, R1 is 19 kilo ohms, R2 is 23 kilo ohms, and op-amp has an output resistance Z0 of 399 kilo ohms. Okay. Now yes. So we need to find out what is the output resistance of the complete voltage regulator circuit. That means how do we find out voltage output impedance or impedance across any node? We say, let's say we apply a small test voltage Vx and it provides a small test current Ix. Then the impedance across that node Vx will be Zx will be Vx upon Ix, right? So here this Ix will split in two parts, I1 and I2, right? So let's say this is a small voltage Vx. So the voltage at this node will be R1 upon R1 plus R2 into Vx. This small Vx will not produce any change across this non-inverting terminal of op-amp, right? So because of this Vx, since there is no change across this node, so we say, let's say it is almost grounded, as its effect is not seen. So let's say if it is a small AC signal, Vx is a small AC signal, so here you'll see that AC signal in the inverting terminal, but the non-inverting terminal will not see any effect because of this small signal Vx, that is an, let's say, a small AC signal Vx. So it is AC grounded, as we normally say. So in that case, if we try to find out what is VD, so VD turns out to be minus of R1 plus R2 into Vx is what is VD, right? So this is VD. Now we have got VD. We know for an op-amp, Vout, that is output, is equal to difference voltage into gain, open loop gain, right? So that turns out to be A0 minus A0 R1 upon R1 plus R2 Vx, right? So if we carefully observe an op-amp, so let's say there is some Z0, here we have V0, and here we have some VA, or let's say it is connected to ground. Let's say if this is the equivalent circuit of your internal circuit of your op-amp, minus plus or plus minus whatever it is. So if we see, this potential is minus A0 R1 upon R1 plus R2 Vx, right? This is less than 0. We know that current flows from higher potential current flows from higher potential to lower potential. So if you think of it that way, so in this particular equivalent circuit that has been drawn, the current will have a direction like this, that is coming towards V out. So the current will have a direction coming out of V out. But here in this particular diagram, if we observe carefully, okay, yes, so if you observe here carefully, we are saying I1 is going inwards, but here it turns out that our current was going outward. So the moment we change the direction of this negative sign over here will go away. Clear? So at this particular node, it turns out that the voltage of the output voltage of op amp is A0 R1 R2 into Vx. This is because of the op amp, the presence of op amp. Its output turns out to be this. Now, since we are taking the current going inward, the current direction to be inward, this output sign can be neglected, and since it is a current, so it will be Vx like V out by the impedance, that is output impedance Z0, right? And that current was going inward, so current ka direction we have changed, so another negative will come. So it will make it plus A naught R1 upon R1 plus R2 times Vx by Z naught. So which makes it A naught R1 by Z naught R1 plus R2 Vx. This is one component. Now what about the next second component of current? The current is Vx, that is the nodal voltage Vx by R1 plus R2. We know the total current coming out of the test voltage source is Ix, which is sum of I1 and I2. So Ix becomes Vx times A naught R1 upon Z naught R1 plus R2 plus 1 upon R1 plus R2, which becomes A naught R1 plus Z naught by Z naught R1 plus R2. If you observe carefully, so Z naught is 399 kilo ohms, whereas R1 into A naught is much higher. It is 1319 times 19 kilo ohms. So it's much higher than 399 kilo ohms, right? So we can neglect Z naught and we can write Ix equivalent to Vx times A naught R1 by Z naught R1 plus R2. So Vx by Ix becomes Z naught R1 plus R2 upon A naught R1. So that is Z naught 1 plus R2 by R1 by A naught. So if you observe this carefully, so let's say R1 upon R1 plus R2 is beta. If we say R1 upon R1 plus R2 being beta, then Vx by Ix turns out to be Z0 upon A beta. And we generally observe and we know that when we apply a negative voltage, it stabilizes the circuit, right? So here output impedance becomes Z0 by equivalent to Z0 by A beta. Similarly, gain also reduces. Stabilization means gain also reduces, right? So gain will also become the initial gain upon A beta. So that's how things turns out. So here, since we got Vx by Ix, so this is the output impedance. Now substituting the values, this was 399 kilo ohms into 1 plus R2 by R1. R2 was 23 and R1 was 19. R2 was 23, R1 was 19 by 1319, right? Yes, 1319. So when we solve this, so we get Z out, that is output impedance to be equal to output impedance turns out to be 658.21 ohms. Yes, this becomes 658.21 ohms. So if we observe carefully, earlier the output impedance of op-amp was actually 399 kilo ohms, but now the output impedance has reduced to 658.21 ohms. So it has reduced drastically. This is because of the feedback circuit that is present. Now moving on to the next question. In this question, it says that in the circuit ever, assume that there is a ripple on the dirty power supply, and the open output allows the ripple through with a gain of 29 dBs minus 29 dBs. Then this gain is known as power supply gain. So as you might remember from the lecture, sir was talking about the gain P, right, which was the power supply gain. This is the same gain, okay, which they are talking about. So P is minus 29 dBs. Yes, sorry, decibels. So it is minus 29 dBs. So yeah, this is P. So basically the power supply gain that they are talking about, that is actually the P that sir was also talking about in the lectures. Now assume that the voltage gain across the Zener diode is constant and does not change even with the ripple power supply. What is the power supply gain of the complete regulator circuit? We have to report in dBs only. So since here we have negative feedback, and as I already mentioned that for negative feedback, gain also becomes the gain also reduces by a factor of A beta. So the new gain will be, so let's say I will say this as P naught upon A times beta. So this will become P naught into 1 plus R2 by R1 by A. So that is 29 times 1 plus 23 by 19 by 1319. Yes, so it turns out to be so we can do one thing. Let's say this P naught is given in decibels, right? And this is power gain. So let's convert into absolute gain first. So this is 29 dBs. So when we talk about actual gain, watt and watt by watt, it will become. So this is actually 10 log base 10 of P actual. So which makes it P actual will become 29 by 10 10 to the power 29 by 10. So P naught watt by watt is 794.028. minus 29 dB, no? Question में it is given minus 29 dB, so it becomes minus, so that is 0.00126 watt by watt. So now when P naught is this much, so we'll substitute actual value into 6. So 0.00126 into 1 plus 23 by 19 by 1319. It turns out to be 0.12311. So yes, okay. So how will we find P actual? It is 10 to the power minus 29 by 10, which turns out to be 0.00126 watt by watt. So after negative feedback, the value that we have got for watt by watt value is this power actual after feedback. Now we want to convert it into dBs, so P in dBs will be 10 log of P actual after feedback. So this will be 10 log P is 10. The answer turns out to be minus 84.515 dBs. Yes. So power supply, power gain turns out to be this. Okay. Wait. This is power supply gain, but it is not power gain. So this is gain because of power supply. So it is volt by volts only. So volt by volt means we'll only use 20 log 10, that formula only. So that makes it so the values will change. So this will become, so yeah, this is not power supply gain, but it's not power gain. You're getting my point. So it is not output power by input power, it's output voltage by input voltage only, but the thing is it is due to the power supply. So it is volt by volt gain only. So that makes it, so when you want to convert it into decibels, we should only use the formula 20 log 10. Is this clear? So we'll only use 20 log 10, so which makes the actual gain to be 0.0355. Okay, this becomes 0355. So yeah, this is 0355. Here also it will be 0355. Yes. Zero 355. So this answer turns out to be 0.0004595, and when we go for 20 log 10 answer, it turns out to be 84.51 decibels. Yes, now it comes out to be 84.51 decibels. So hope this is clear. So this was power supply gain, but this gain is actually V out by V in. So this is voltage gain only. So when it is a voltage gain, at that time when we go for decibel conversion, we'll use 20 log 10 only, right? So we'll go for 20 log 10, and final answer that we'll get in decibels is minus 84.515. So that was the mistake. Now hope this is clear. And so moving on to the next question. So this is question number 1. Question number 2. So these two questions were based on the same circuit, right? Now we are going for another question, which is question number 3. So in this circuit, below, the inductor and the capacitor are so large that the current through the inductor is constant. So given that ID is constant and voltage across the capacitor is constant, so voltage across capacitor VC is constant. The MOS is in saturation all the times. So for saturation, what is the condition? VGS should be greater than equal to, VDS should be greater than equal to VGS minus VTH, or should be greater than equal to V over drive. VDS should be greater than equal to V over drive. So minimum VDS can be, so VDS min, which is VD here, it can be V over drive, and VGST is basically the overdrive voltage. Okay, so it is given by 0.15 volts. Power supply VDD is 1.9 volts and R is 0.9 kilo ohms. So the question that has been asked is, what is the maximum amplitude of VD chosen such that the device is in saturation? What can be the maximum VD so that the device is saturation? So here VC is a constant value. So that means VC is, let's say, completely charged and it has a constant value. So what is the maximum charge that VC can have, or what is the maximum voltage VC can have is 1.9 volts, right? So it can be completely charged. And since VD is, so what is the maximum value VC can have? Maximum VC can have VDD. But here, so think of it as a voltage divider circuit, okay? So here it was VDD. Now that VDD gets distributed in this branch and this branch. So now since there will be two currents flowing through these two branches and these currents will be distributed. So if uh, 0.15 is the voltage which is across this transistor, this has 0.015, then what can be the maximum value that our VD can get? So VD can get maximum, that is VDD minus the voltage that is dropped across the transistor, right? So the maximum voltage that VD can have is 1.75 volts. Okay, now next question, coming to the fourth question. So this is the continuation question. Here it is asked that while VD is maximum, so while VD is maximum, so we came to know, right, what is the maximum VD we can have. So maximum VD, that is of 1.75 volts. What is the maximum amplitude of ID such that the device is always on? Now small ID. What is small ID? Small ID is what is the maximum amplitude of ID such that the device is on? So that small ID will be VD by R, right? So the current in this path, so what will be the current in this path? This will be VD by R. So we'll simply put 1.75 volts by 0.9 kilo ohms, and we get ID as 1.944 milliamperes through resistor R. This is the current through resistor R. Now next question, it is again the question in continuation with the previous circuit itself. So in this question it is given that assume ID to be GM times VG even for larger amplitudes. So ID is given as GM VG. Now what is the required GM such that ID is achieved when the amplitude of VD is maximum? So we know that GM is 2ID times 2ID by VOV, right? 2ID times VOV. ID is 1.944 milliamperes. VOV is 0.15 volts. 0.5 volts. Let me copy this diagram also. Okay. So yeah. So it is said that let's say ID is denoted by GMVG, and since we know GM is 2 ID times VOV, VOV is already known to be 0.15. So GM becomes 2 times 1944 by 0.15 milliseconds. So GM becomes 25.926 millisiemens. This is the value of GM that we'll get. Now another question. So this was question 6 for today's session. So in this question it is given that ID is K times Vgs minus Vt whole square. What is the corresponding value of K? Give your answer in millisiemens per volt, right? So we got ID to be 1.944 milliamperes, right? In earlier question we have already solved ID to be 1.944, and we know Vgs minus Vt, that is VOV, to be 0.15. So K becomes ID by VOV square, so that is it's 86.4 millisiemens per volt. So this is what the value of K will turn out. So all these questions were based on the single circuit, whereas the above two questions were based on this particular circuit, that is open based regulator. Now there is something I would like to discuss which is related to this op-amp based regulators only. So maybe, yeah. So for op-amp based regulators, we observe that the gain becomes A naught upon 1 plus, or so like here the gain was power supply gain, it was, right? So let's say talking about power supply gain only, became P naught upon A beta, or even Z out became Z naught upon A beta, right? So now if we look at the frequency response of an op-amp, so how it looks like. So frequency response of an op-amp looks somewhat like this, right? So it maintains its value, a constant value. Then as frequency increases, it its gain reduces. So if you observe now after feedback, these are after negative feedback, so what will happen for the case of gain, as we increase the frequency is increasing, it will reduce the P naught, that is open loop power gain, power supply gain. Okay, open loop power supply gain will reduce, or open loop gain, if I talk about A naught in general, this will reduce. So now what will happen, your denominator will start reducing. So your feedback gain, that is this gain which I'm talking about, let's say this is G. So this G actually starts increasing. Can you observe that? I hope this makes sense, right? So और इसको P naught की जगह we can say और G naught also. Okay, or whatever we want, or let's say Z naught ka we are talking about. So when we increase the frequency, what happens is this A naught will reduce. The reduction in A naught will actually, so earlier the Z naught was less, now the Z naught will start increasing as the denominator is reducing, right? So this is how the frequency response changes after the negative feedback. Hope this is clear. So what I would like to say is the frequency, so earlier we were thinking of certain trend, but now the trend is not the same. So with frequency, due to the gain in denominator, the gain in denominator, the frequency response becomes opposite. Considering earlier the Z0 was constant without feedback, now the Z0 will show opposite trend of that of gains frequency response because of this particular expression. That is one more thing that I would like to add. And with this, maybe we can conclude this session. And if you have any doubts, you can feel free to comment below the videos, and I'll also post this PDF in the drive which was shared with you earlier. And with this piece of or with this set of questions and discussions, we'll conclude the course of analog electronic circuits for this semester. And hope these lectures or these sessions help you out in some way. And all the best to all of you for the upcoming exam which you'll have for this course. And that's all for today. Thank you. Have a wonderful day ahead.